All right, so y'all got the general gist of what's going on with our VSEPR, our valence shell electron pair repulsion models. I'm gonna move pretty quickly through the next portion. When you draw it, you'll have a central atom, and another central atom, and another central atom. We'll just kind of go through as we go. If you end up with two effective pairs around the central atom, the only way two things will be around the central atom, is linear. That's it. 180-degree bond angle. That's the only way two things would fit around that. So that's an easy one, linear. So a good example of this would be like carbon dioxide. Carbon bonded to an oxygen, bonded to an oxygen. We got our lone pairs over here. And even those are double bonds, they're in the same location, two things around the central atom. This just gonna take practice. I'm moving through fast this time. So two effective pairs, we've got linear. Three effective pairs, 1, 2, 3. Example of this, remember boron is an exception. Boron is fine with 6 valence electrons, so boron bonded to fluorines or hydrogens. This would be a trigonal planar 120-degree bond angle. All right, and 120-degree bond angle, trigonal planar shape. So imagine if I have three things around the central atom, those three things, they'll have the minimum number of repulsions with 120-degree bond angles. If one of these was replaced with a lone pair, which would happen, typically you're gonna see that with a double bond over here. So you'll have three things here and a double bond here. So let's say this is an oxygen, this is a hydrogen, it's a lone pair there, this is a carbon. If you have something like this, this would be a bent shape. So imagine if I take this and the yellow is just a lone pair. So it's just sitting like this, you can see the molecule's bent. It would be a linear if it's just two, but this negative charge bends it. So that's a bent shape. And this is like a 114-degree bond angle, not really a big deal. 4 effective pairs, we've already talked about it. 1, 2, 3, 4, tetrahedral. 1, 2, 3, 4, trigonal pyramidal. One of them's a lone pair, 4 effective pairs. And 1, 2, 3, 4. This is a bent shape. 109.5 to 107 to 104. Lone pairs, push them, squeezy, squeezy, squeezy. So those are our basics for VSEPR models. We will be talking about expanding octets, and we'll talk about how that kind of keeps going with it. Now, with that being said, all of these shapes, we're going to talk about something called polarity. This is something I have talked about to you guys hundreds and hundreds of times, so you should be really good at it. When we look at these shapes, if we have, let's say, carbon with all of these guys around the central atom being the same, we would say this is a nonpolar molecule. The electrons that are being shared around the central atom evenly in all directions, there is no net positive negative charge across this molecule. As a result, there is no net positive negative side. And so what happens is if a nonpolar molecule and another nonpolar molecule come together, there's gonna be very little positive negative attractions for them. And we're gonna come back to that later, but that's what's called London dispersion forces are the only types of forces there. So you typically see nonpolar molecules being gases, or they have to be really big nonpolar molecules to be more solids. Even then, they're gonna vaporize pretty quick. So when we look at that, we would assume this guy would be a nonpolar molecule. When we look at something like ammonia, because it's not even across the way, we would assume this guy would be polar. And that means that we're gonna have a partially negative side, partially positive side, partially positive side, partially positive side. And what does that mean? That means when it comes in contact with another one, that partially negative side and the partially positive side will attract. There will be, there will be intermolecular forces attracting them, partially positive to partially negative side. That means there's gonna be more force holding them together. So you tend to see these things maybe being liquids, maybe being gases that can, it just gives them a mechanism to come together. Maybe being solids, whatever. That doesn't really matter. That has to do more with temperature, but it's the idea that it gives a starting spot. It gives something for them to be attracted to in order to actually come together in the first place. It's just built into the system, if you will. So when we look at the VSEPR models and we look at things like linear shapes, and we look at things like trigonal planar shapes, and we look at things that are tetrahedral shapes, we assume these guys would be nonpolar. And that means that they're not going to have a lot of attractive forces between one and another nonpolar molecule. When we look at something like this, or something like this, or something like this, built into the system there, it has a partially negative and a partially positive side. This side has more electrons on it, more negative. The electrons might be being pulled this way, more electronegativity, positive sides, and that kind of builds into the system some positive negative attractions between one molecule and another molecule. And so we call them intermolecular forces. An interstate highway is a highway that goes from one state to another state. So an intermolecular force are going to be attractive forces between one molecule and another molecule. And that has everything to do with states of matter, melting points, boiling points, all that good stuff, all that, and mechanisms of how they can actually interact with each other, how they're going to hit each other. Now, with that being said, if we go back to our tetrahedron here, and if I have myself a fluorine here, and then a hydrogen, and a hydrogen, we could assume this guy might be polar because it has a difference on one end. And that means that the electrons will be shifted slightly. It won't be evenly shared. One of the ways we talked about it in class was, imagine if I had this guy firing a rocket this way, firing a rocket this way, firing a rocket this way, firing a rocket this way. If they were evenly spaced and going in complete different directions from each other, and they all fired at the same time, we'd expect this ball just to sit here. But then if I replaced this rocket with a much more powerful rocket, even though it's a tetrahedron shape, when these fire, we would expect this guy to push this guy downwards. Or you can, replace it. That's not as easy to see. We'd expect this guy to push, and even though these guys are pushing this way, it would go slightly that way. I don't know if that helps, but the idea is that what we want is we want even pulls on electrons there. We spent a lot of time on this in class. So basically this whole section, we're looking at all the shapes that are there, and we're looking at if they are even around that central atom, we would assume the thing is nonpolar, which means there's not going to be a lot of IMFs, intermolecular forces. And if it is uneven, then we would assume the thing is polar. We're going to get more into details on that later.